Thanks. So I'd like to start by thanking the organizers for inviting me to come to this great place and tell you about work I've been involved with recently, studying the possibility that supermassive black holes actually had seeds that were themselves supermassive in scale, supermassive stars in particular. This is a list of collaborators that are going to who I've worked with and the things I'll present. I'm also going to include a variety of work from other people, from other groups that I think supports what we've been finding. Time allowing, of course. So to start after lunch, maybe some pretty pictures to ease into it. The ubiquity of supermassive black holes, just a reminder that the formation of black holes is intimately related to the formation of galaxies. Understanding how supermassive black holes form is critical to understanding how galaxy formation fits into cosmology. Every massive galaxy is believed to have a supermassive black hole at its center, including our own Milky Way, which has a 4 billion solar mass black hole at Sag A star, and even some outlier galaxies, such as that presented by Rimco recently, have enormous black holes of 10 billion solar masses or so. And so understanding where these come from is clearly critical. This is a nice figure I've taken from Marta's recent review in Science. I won't dwell on this because we've heard a lot about these different pathways already today. POP3 stars, sort of run-of-the-mill POP3 stars, which may have initial black hole seed masses of around 100 solar masses or so, are one of the possible avenues for the initial process of seed formation. And another one is supermassive stars, which actually form from primordial gas themselves, but primordial gas that remains at a high temperature for reasons I'll come to, which results in the formation of a supermassive star with 10,000 or up to 1 million solar masses or so. And then finally, there's another idea that dense stellar clusters may form, and the stars may merge to form around 1,000 solar mass black hole seeds or so. But I'm really going to focus on the supermassive stellar avenue for this talk. So to give you a brief outline, I'm going to tell you, first of all, why we believe supermassive stars may really be the strongest candidates to explain supermassive black holes, especially at the highest redshifts. Explain some of the work that's gone into modeling the growth of these stars and their evolution. Give you an idea for what the prospects are for detecting them, either via direct imaging or maybe from the chemical signature they leave behind in the event that they actually, in some cases, explode as supermassive supernovae, which is a recent possibility that was discovered, and we've been working on Los Alamos and elsewhere with collaborators. These actually would have been the biggest explosions in the universe, which makes them interesting to study in their own right. So I've taken the liberty of sort of presenting in this slide the question that we have to deal with in terms of explaining the presence of the most massive black holes at the highest redshifts, sort of comparing what the picture was 10 years ago to what it is now. And just going to highlight a couple of the differences in the picture we have. 10 years ago, we knew that from the Sloan Digital Sky Survey that there were black holes powering quasars at redshift 6, which had masses of the order of 1 billion solar masses. This is just shy of 1 billion years after the Big Bang. In terms of the seeds for their formation, we had cosmological parameters from the first year WMAP data suggesting that population 3 stars formed around redshift of 30, maybe 100 million years after the Big Bang or so. And in between here, this is our starting point, this is our ending point, our target for explaining the most massive black holes that present the greatest challenge to explain at early times. This really defines what I would call the epoch of rapid black hole growth in this case. If we fast forward to the picture now, there are a couple of things that are different. First of all, we know now about quasars at even higher redshift that are powered by billion solar mass black holes. 2 billion solar mass black hole reported by Mortlock et al. At redshift 7, just under 800 mega years after the Big Bang. At the same time, our cosmology has been refined from many years of taking data with WMAP and also from Planck, telling us that population 3 stars probably formed somewhat later than we thought previously, maybe typically more like redshift 20, about 200 million years after the Big Bang. And the thing to highlight really is this window for growing the most massive early black holes is shrinking on us. So we had a challenge 10 years ago to do this, and now the challenge is just getting more difficult. And when you look at the theory behind this, one of the questions you're quickly drawn to really is what's the mass? What's the initial seed black hole mass? As we've heard a lot today, the more massive your seeds are, the easier it is to grow a black hole to give a mass in a given time. So this is really the main motivation for thinking about supermassive stars as the seeds. I made the schematic plot here just to highlight what it buys you in terms of explaining, for instance, the highest redshift quasar, redshift 7, reported by Mortlock et al. This is the mass of a black hole as a function of time since the Big Bang. These are the starting points for population 3 seeds, about 100 solar masses, 200 million years after the Big Bang. Supermassive stars would have formed later, but much more massive. And if you consider Eddington limited accretion for sort of standard assumptions about radiative efficiency and things like that, what you find is that supermassive stellar seeds can get you to this mass. The population 3 seeds really encounter a lot of challenges. And so this is one of the, just to highlight the main motivation in sort of basic cartoon format. Here we can look at the picture a bit more quantitatively. This is a plot from a recent paper published in AppJ where we're looking at the formation, for formation sites appropriate for supermassive stellar seeds at the top and then for population 3 seeds at the bottom. We're plotting here the initial black hole seed mass that you need in order to explain growth to a given, in order to explain the growth of a billion solar mass black hole by redshift z given on the x-axis. And what I want to highlight here is that, and again I can plot this most challenging quasar redshift 7 to explain, for various radiative efficiencies of accretion, the answer changes wildly. So just to take this case at the top, you could say you can grow this black hole by redshift of 7. If you have a low radiative efficiency of 0.07, 7% of the radiation, or sorry, 7% of the mass accreted onto the black hole being converted into radiation, you can appeal to very low mass seeds, below 10 solar masses. Whereas if you have a high radiative efficiency around 0.15, you're pushed to consider 100 solar mass seeds right off the bat. And this is already assuming constant Eddington limited accretion. The thing is that I want to point out in the next couple of slides actually is that radiative efficiencies that have been reported in the literature are actually quite high, which pushes you to consider more and more massive seeds. This, along with a lot of other theory, I think provides some support for this idea. So observationally, over the past 10 years or so, there have been a lot of groups that have claimed that to match observations of high redshift quasars, you have to appeal to radiative efficiencies of something like 0.1 or 0.15 or even higher. There have been trends suggested of increasing radiative efficiency with redshift and with the mass of black holes. Sorry, this word is off. And in some cases, values as high as epsilon of 0.3 or 0.4 have been estimated for very high mass black holes at high redshift. This is a plot from Wang et al., just to give you a flavor for what the data they're presenting looks like. You're looking at radiative efficiencies here in excess of 0.3, back to redshift of 2 at least. And this is way off the charts of what I was showing before, which I think is something that has to be taken into account. We need to really get a handle on what radiative efficiency is because it changes the answer in terms of initial seed mass by orders of magnitude pretty quickly. So it's not just observations. Actually, there's a growing body of theoretical or cosmological simulations where people are tracking the radiative efficiency of black holes by tracking the spin of the black hole. This is a plot I've taken from Johan's recent paper where they find that the black hole is actually spun up fairly efficiently because it accretes, the spin stays aligned with the angular momentum of the gas that it's accreting. And you can see there's a trend at high redshift to have very high radiative efficiency, again around 0.3 or so. So this is very hard to accommodate actually. And I think we have to understand how to do that. I wanted to mention also there's an additional challenge for especially low mass population 3 seeds. If you're looking at 100 solar mass pop 3 stars collapsing to black holes, and this will be touched on more in the next talk, I think, the radiative feedback is actually fairly vicious. And this is a cosmological simulation from Young-Wan et al. And they plot up here the accretion rate they find for accretion onto pop 3 seeds, and you can see it's down here at about 1/1,000,000th of a solar mass per year, which is about a factor of a million below what you need to grow something to a billion solar masses within the first billion years. So there are a variety of challenges, especially for low mass seeds. This is something that we sort of summarized in our recent paper. I should tell you what's plotted here. This is the number density of supermassive black holes at a given redshift, with a billion solar masses in particular, as a function of redshifts here. These are points from the luminosity function, derived from the luminosity function from Shankar et al. These are SDSS quasar number density lower limits. The lower limit you get from Mortlock et al. Redshift 7 quasar. And these lines are what you can accommodate in terms of radiative efficiency, assuming two different formation sites. That is, in 10 to the 7 solar mass halos where you expect supermassive stars to form, and 10 to the 5 or so where you expect population 3 seeds to form. The bottom line here is that for the low mass seed case, you can grow the most massive high redshift black holes, but you need to appeal to constant Eddington accretion, and you also need a low radiative efficiency, which there is not a tremendous amount of evidence for, I don't think. So these things aren't clearly in evidence, which really leaves you as the massive seeds as the most consistent, simplest explanation. So supermassive stars are really exotic objects, right? We've never seen one. It's sort of hard to imagine a star 100 million times more massive than the sun. So how much credence should we really put into the theory? Well, I want to argue that actually the ingredients you need for supermassive star formation are not that hard to come by in the early universe. So I made this comparison of sort of standard population 3 properties of formation site, the coolants that are important for the gas, the temperature of the gas from which the star forms, accretion rate onto the star as it's growing, typical final masses, and the possible end states for standard Pop3, and then over here for supermassive Pop3. The main difference here really is highlighted, which is the gas coolant. If you can destroy somehow H2 molecules in the gas, you're left only with atomic hydrogen to do your cooling, which forces you to form in more massive halos with higher virial temperatures around 10,000 Kelvin. Right away, from dimensional arguments, you see the accretion rates are going to be maybe a factor of 1,000 times higher. You're going to grow the object to orders of magnitude larger masses than in standard Pop3, and you'll have these different interesting end states, including very massive Pop3, black hole seeds. So this is the main thing that you need, really, to first order. You have to destroy H2 molecules. If you can do that, hierarchical structure formation will give you something like a supermassive star. So what does it look like? This is a cosmological simulation we ran a few years ago now, where we're tracking the collapse of this hot primordial gas under the assumption that H2 cooling is not present, that H2 has been dissociated by an H2 dissociating background radiation field. The gas stays at around 10,000 Kelvin or so, and when it collapses into the center of this halo, the central object that formed accretes at rates between 0.1 and 1 solar mass per year. So these extremely high accretion rates are borne out in cosmological simulations. And it's not just our group. There's a number of groups now that have done even higher resolution simulations. This is from Latif et al., who've used ENSO to do that. And they've found, again, they're looking at the dense cores that are formed in the middle of these halos, and they find, again, these very high accretion rates. So this is a fairly robust result in this type of primordial gas that's cooled only via atomic hydrogen. So one question you might have is, what about radiative feedback from the stars? If you're growing stars to supermassive scales, there's a lot of energy that can be liberated in the form of radiation. Maybe they stop their own accretion because the radiation pushes the accretion field back, and this may prevent you from growing a star to these really high masses that we're talking about. This has been studied by Hosokawa et al. Recently for the case of protostellar evolution under extremely high mass accretion rates. Here, these purple lines are for 1 solar mass per year. This is the effective temperature, effective surface temperature of the star as a function of mass as it grows. This is the radius of the star. What they find is that the star stays fairly puffed up. The surface temperatures are low, and that means that UV feedback, radiative feedback, is fairly weak. And they have no problem growing the star to 1,000 solar masses at least when they stop their simulation. But this does beg the question, what about going beyond 1,000 solar masses? You need to get to 100,000 or maybe even 1 million. And this is something that we addressed in Los Alamos. This is a plot from our recent paper. This is the maximum stellar mass, what you call sort of the final mass a star can achieve as a function of the rate at which it accretes gas, assuming it accretes gas at a constant rate until radiative feedback stops accretion. And that happens along this blue line here, which we call the feedback limited case. And I just want to point out that for the high accretion rates found in cosmological simulations across the board, you can see that radiative feedback doesn't stop the growth of these objects until they grow to at least 100,000 or 1 million solar masses. And I want to point out, especially this is under very strong feedback, assumption of very strong feedback, that the star enters the main sequence, has a surface temperature around 100,000 Kelvin, and really blasts out high energy radiation. there's no way it's even in that case that it's stopping accretion to these high masses. So it seems like if you have the conditions, if you have the conditions in place for the formation of these supermassive stars, that is, you can destroy H2 molecules and prevent cooling, that there's nothing that's going to stop them from forming, not even their own radiation. But how often do they happen in their universe? Is there only one per Hubble volume? Or do they form in abundance, high enough abundance that we can start to explain lots of supermassive black holes via this mechanism? So to get at that question, you actually have to go to fairly sophisticated cosmological simulations because you have to track a number of things. You need to track metal enrichment because you care about primordial gas, and you don't want it to be enriched with heavy elements. You have to track the radiation field because you care about H2 dissociating radiation. Both of these things vary in space and in time. You need to keep track of population 2 and 3 star formation because the spectra from the different stars has an important impact on H2 photodissociation. And this is something we were able to do with Claudio Della Vecchia and Sara Kochvar back at MPE. This is a really nice movie that Claudio made of one of the simulations that we ran with all this physics included. So we can go into the simulation and look and see, are there sites where you could form supermassive stars? What you need, again, is primordial gas that's collapsed to high density in atomic cooling halos. It's not metal enriched at the same time. So we had actually a really surprising result. In just a 4 megaparsec co-moving simulation volume, we find 6 candidate supermassive star host halos. So this is really surprising. Just a few years ago, people were trying hard to come up with models in which you could form one of these objects in a cubic gigaparsec, right? And now we're forming 6 of these in a volume, a million times or more smaller than that. Of course, not all these are expected to grow to supermassive scales. You don't necessarily violate the mass budget of black holes. But this is an important problem. Do we really produce this many, or do we need to invoke something to not produce as many? So there's sort of a shift here in the questions we have to ask. This has been studied in detail by Bhaskar Agarwal. I refer you to his poster outside on this. This is a snapshot of the simulation. This is the metal-enriched patches here. This is the radiation field as a function of space. You can see how it varies around star-forming galaxies. Up here, this is the H2 associated radiation field to which the halos are subjected as a function of redshift, and you can see outside on Bhaskar's poster how actually star formation is suppressed until you form one of these objects, possibly. So star formation, supermassive star formation appears to be perhaps much more common than we thought in the past. With this slide, I just want to make the point, actually, that even by doing things like varying the physics we include in the simulation, changing the star formation efficiencies, changing the escape fraction of H2 associating photons, things like that, in every case, what we find when you plot the number density of supermassive stars in the sky as a function of redshift, which is shown here, all these lines lie above what you need in order to expect to find one of these objects within the deep wide survey area that James Webb is going to survey. So there's a possibility that James Webb may be able to find these objects. And they're interesting spectral signatures as well that you should feel free to ask about if you'd like to. So this is one way we could hope to find these objects, is by just imaging using James Webb and picking out and getting lucky and having one or a few of these in our field of view. There's another interesting possibility that's been recently discovered by Alex Hager, who's run stellar evolution calculations for supermassive stars. And his group has found that in a mass range around 50,000 solar masses or so, the star actually encounters explosive nuclear burning, which results in complete disruption of the star, and an explosion with an energy approaching 10 to the 55 ergs. So this is 10,000 times more energetic than typical supernovae today, and these would have been genuinely probably the most energetic thermonuclear events in the universe. So it's an alternative endpoint for stellar evolution. You don't form black hole seeds this way, but these explosions could give us a way to get a handle on whether or not supermassive stars inhabit the early universe. So what we did, following on Alex's calculations, is actually put the findings from those in terms of sort of the velocity profile of the explosion, the density profile. We've placed it into the proper cosmological setting, one of these atomic cooling halos, and we've run the simulation forward using Gadget to see what happens in the cosmological environment when one of these extremely energetic explosions takes place. So this is a movie showing what we found. This is the number density of the gas. This is the radial velocity, temperature of the gas, free electron fraction. You can see all this is shock ionized to very high temperature. The velocities you achieve are of the order of 1,000 kilometers per second or so, already at the virial radius of the halo. So you're blowing gas way out into the intergalactic medium and polluting the gas with a large amount of metals, actually. We find also that the gas recollapses into the center of the halo, which presents an interesting possibility of star formation from that metal-enriched gas. So as I said, there's a lot of heavy elements that are produced. You have about 20,000 solar masses and heavy elements unleashed in one of these explosions. It recollapses in the center of the halo. You can see that in this plot. This is the average metallicity of the gas as a function of distance from the center of the halo at 3 different times after the explosion. At 1 megayear, it's all fairly well contained within the virial radius, around 1,000 parsec, and then it sort of spreads out, and also some recollapses back in. The average metallicity of the gas is about 1/20th of the solar value, which is interesting because this is much higher metallicity than have been found, than the most metal poor stars that have been found that are assumed to be the most primitive. And this means that actually surveys that have looked for the most metal poor stars could have missed these objects. And maybe this is one way, by looking at the stellar archaeological record, that we can get a handle on whether or not supermassive stars existed in the early universe. And there are I'm not sure if they're completely unique chemical signatures, but there are chemical signatures to look for. So this is my last slide, actually, just quickly, because I want to get to discussion section and so forth. These explosions are extremely bright, of course. They're very energetic. They're bright enough, actually, to be seen by the James Webb Space Telescope out to about redshift of 30 or so. That's the limiting magnitude here. This is, I should point out, this is not absolute magnitude. This is current magnitude. Also, for the Wide Field Infrared Survey Telescope, WFIRST, you could find these objects out to redshift of 20 or so. It may well be that they typically form even lower redshifts, which means that WFIRST might give you the best chance because this is an all-sky survey. They're very rare objects, so you need to look over the whole sphere of the sky if possible. And so this may be another way, actually, to identify the remnants of supermassive stars as well. So I'll leave you with my conclusions here. I think there's a strong argument, given the data we have in our hands today, that supermassive stars may well be the best candidates to explain supermassive black holes, especially in the early universe. Nothing seems to stop their growth once the conditions are set for them to form. They may be common enough to be detected by James Webb or in the fossil record of low metallicity stars in our galaxy, if indeed supermassive supernovae actually take place in some cases. And I'll leave you with this movie of one of these biggest explosions. Thanks. Sure. Oh.
Okay. So if these black holes are accreting at more than 10-30% of Eddington, you're not in a Shakura-Sunyaev disk anymore. So you may have a lower radiative efficiency compared to what you calculate, just assuming converting spin to radiative efficiency. So super or close to Eddington models of disks haven't been studied as much in detail as ADA for RIAFs.
Yeah, I see.
But this may be one of the ways to reconcile the various
Yeah,
issues.
I think that's a great point. We may have to appeal to something like that, actually, I think.
Yeah. Very nice results. I'm just curious. So what sounds like a very large region is polluted. So what fraction of the universe gets polluted with metals, say at redshift 7, redshift 6?
That's a really good question. To answer it, I'm afraid we have to know the IMF of supermassive stars, which we don't really have a great handle on. I think it's quite rare. It's definitely a pertinent question in terms of the fossil record, because if you don't have one of these going off in the cumulative volume of the Milky Way, then you won't find it. So actually, that's a good question for future work. I think has to be dealt with. Oh, sure. Yeah, that's also true. Yeah, you're right. That's true.
Raffaella, maybe Elena can join.
Yes, Jarrett. Can you elaborate a little bit more on the number density of these supermassive stars that you find in the simulation? So what is the key that has boosted so much the number of
so one of the things that's changed over the past few years, I think, is the assessment of how high a Lyman-Werner background you need to destroy molecules effectively enough. That comes down to, I think, the realization that actually population 3 stars have a spectrum which helps you destroy H-, which is an intermediary for the formation of H2. So this opens up the possibility that around population 3 star forming galaxies that you can achieve the flux that you need a lot more easily than we thought in the past. I think some would maybe also associated with that is better modeling of shielding of H2 molecules. But basically, the limits that you need in terms of flux have come down. I think that's the main thing that's different. Of course, the modeling, including metal enrichment and so forth in a cosmological setting, wasn't done yet before this either. But I think that's why we're finding so many. If that's the question.
Okay, so there is trial. Elena, can you read it?
Yeah, just to expand on that, what would be the rate of supernovae, and can you imagine detecting these things, and how would you do that?
What would be the rate of these?
Yeah, and the rate and the flux. So, what kind of observational signature would you have of this?
Sure. So in just this last slide, these are actually Likers that have been calculated using a radiation hydrodynamics code called RAGE at Los Alamos. This isn't Whalen et al. And these are what you expect for in our frame, for the observer frame, in terms of a magnitude for various redshifts at which these could occur. So this is how we come to the conclusion that you can detect some out to 30 and 20. I guess in terms of a unique signature, I think it's hard to come up with something that's this bright at those redshifts if you can pinpoint the redshift. Beyond that, I don't know details actually. Oh, well, in terms of the rate here? Yeah, it's really open. I mean, actually, the mass range in which Alex Hager finds these to occur is apparently fairly small. So you have to convolve that with the IMF and the formation rate of these stars. I think it's very difficult actually. But in all sky survey, you have the best chance possible.
There was again a question back, and then Lucio, and then you. So then Lucio.
So I haven't understood clearly what is your definition of supermassive star in the simulation. So how do you actually define?
So in the simulation, we basically just identify regions where the conditions are right for their formation. I believe if that's what you're getting at, and not in all these do we actually put a supermassive star in. In one of the early simulations, we put a black hole in one of the first movies I showed. But really, we're just looking at regions where you have primordial gas collapsing to high density under the influence of a high radiation field, which are the basic ingredients.
It's a Jensen-stable blob that you have at the end.
Yes. If you go to high enough resolution, you see a runaway gravitational collapse.
But you can't exclude that you would have fragmentation below a certain scale due to angular momentum.
That's a good point, actually. Yeah. I think that has to be worked out with higher resolution simulations. I was talking to people earlier. I think that this sort of study of supermassive stars is sort of at the point where the study of population 3 stars was 10 years ago, where everybody thought that they were 100 solar mass, 500 solar masses, and they all formed one per halo.
Yeah, that's
sort of where we are here. It has to be refined. But I think it's true that we can imagine easily that they're much more massive because the temperatures we know must be higher, accretion rates must be higher.
So, sort of a very general question. So we hear about this radiative feedback thing.
Yeah.
Is there any observational evidence of radiative feedback? And if so, has there been any comparison with theory? Because it's being talked in theory all the time.
Yeah. In the early universe, a lot of the time I think it can be tied into the history of reionization. In the sense that, so the photons that you need to destroy H2 molecules have an energy just below what ionizes hydrogen. So if you look at an reionization history, that tells you something about what the photodissociating flux might have been as well. So you get some limits.
So I guess my question is like more general. So
okay, yeah.
Whenever we talk about feedback, we have this picture of jets, beautiful jets in clusters or winds and stuff.
Yeah, a picture of what, yeah, sure.
So I'm thinking about something.
Yeah.
So is there something such ubiquitous in the case of
maybe
feedback?
Maybe if I have just a minute, I can flip back to a slide with Bosker's result. So this is one way to picture it. This is a slice in our simulation volume. This is actually what you're looking at here. Maybe I didn't explain it. I went fast. This is the radiation field as a function of space here. This red point here is actually a star-forming galaxy producing the radiation. So you can see it's basically falling off as R squared. We've done a simple prescription here. You can see that it's additive though, right? So there are two star-forming galaxies, and in the middle you'll have a higher radiative flux. So this is one way to think about it. And it's really just radiation produced by stars that pervades a cosmological volume.
Mm-hmm. Yeah. That's again more general. So is it possible that there could be like any signal from these supermassive stars, these seeds in the cosmic X-ray background or something from the accretion that they're doing?
Yeah, I think it's a possibility. Mm-hmm. Certainly, yeah. And that gives you some kind of limit too, I believe.
That should be limit like a statistical thing, like a power spectrum or something, yeah.
I think that's true, actually, yes.
So I was wondering about the structure of the star that you explode.
Yeah.
So, for instance, how massive is the core, or how much fuel get burnt, and if it's relaxed or not. I'm asking just because the pre-star in the path to black holes, probably it's not a classic star. So, for instance, it's convectively stable, it has a very small core, and so on. So, maybe the mass of the core enters in the metals you produce. So.
Yeah, that's actually true. So, and this is something we've been bugging Alex Hager about for a while, actually, because the simulations he's done, stellar evolution calculations, I believe, assume that you have already in place a massive star. So it's not really done self-consistently in terms of something that has to accrete during its life, which would give you something maybe more like a quasi-star at the end of its life, possibly. So you need to get to a main sequence phase, which is possible if the accretion rate falls off during its growth. But actually, I think we have to take the explosion calculation with a grain of salt because it's not a completely consistent calculation. That's certainly fair criticism.
Well, I have a question. So back in the early days, 10 years ago, I knew that you have a pair instability when the mass is in between 140
and
260.
Yeah, that's right.
So now we have stars that are exploding and have a mass of 50,000 solar masses.
Well, we may.
Or what? Okay. So the question is. Do you really explode the entire star? Do you have a relic, and how does this depend on the metallicity in any case?
Yeah, so Alex's calculation, he finds that the star is completely disrupted. Actually, it's sort of marginal. The interior, I think, is the outward velocity is barely above escape, but there should be no relic, is the prediction. Actually, yeah, that's right.
So. Are there other questions? Well, if not, thank the speaker again.